In this video, we're going over the concepts of chapter 3, which is titled Compounds Putting Particles Together, Part 1. In these videos for this chapter, Part 1, we are going to go over specifically sections 3.1 to sections 3.3. Before we talk about compounds, we should talk about the elements that specifically come together to make compounds. And we are going to first look at the history of how we can actually look at the structure of an atom. When it comes to defining what an atom is, it is the smallest particle of an element that retains the characteristics of that element. An example of an element is aluminum foil. And you can see in the top right corner that there's an image of aluminum foil. Aluminum foil is made out of aluminum atoms. And we can observe that this image specifically illustrates the shape of an atom and how would ideally we think about aluminum atoms being present in this substance. When it comes to how we came about knowing what the structure of an atom, we should talk about important experiments that gave us the insight into the structure of an atom. Everything starts around 400 to 300 BC with the Greek philosopher Democritus. So during that time, there were different Greek philosophers, including Aristotle and Democritus. But Democritus, different from the other philosophers, he actually proposed an atomic theory that defined that atoms were tiny, hard, and uncuttable shapes that will define the substances that were around them. So the way that he visualized these is that atoms, for example, the ones that are present in water, will have round shapes just because when you observe the behavior of water, it actually flows. Now, it took about 2,000 years later for John Dalton in around 1803 or 1803 to actually propose experiments and prove experimentally that indeed the substances around us were made out of atoms. He saw, or he proposed, that these atoms were solid shapes, that they were indivisible, and he viewed them as spheres. Through experimentation, he saw that these atoms could not be destroyed or reconstructed. Many years later, in 1897, J.J. Thomson started investigating if this particle called atom that was present in elements was the smallest unit that could be found. In his experiments, he saw, specifically his experiment is called the cathode ray experiment. He saw that an atom could be hypothesized to be a sphere that had positive charge, but it had subatomic particles, which he found to be negatively charged. So when it comes to atoms, he actually was the one that discovered the negatively charged particles that to date we call electrons. Because during that time, people understood that if you have a negative charge, which in the illustration that we have here are going to be these balls that I'm highlighting in black, in green, those are the electrons. And we knew that those electrons cannot be living freely. They need to be contained in a positive charge. He assumed that they were going to be kind of stuck in a dense positive area. That's why his atomic model sometimes is referred to as the plum pudding model, And this comes from a dish that if you want to relate it to something that maybe you're familiar with, it would be kind of like looking at fruitcake or looking at a blueberry muffin, where the blueberries in the blueberry muffin will be representing the electrons, and the muffin itself, the batter, the cake, if you want to call it that, will be representing the positive charge area. A few years later, Rutherford performed an experiment that is called the gold foil experiment. And in the gold foil experiment, he wanted to investigate, okay, since J.J. Thomson discovered electrons, and we know that there's a positive area, later other scientists looked at the existence of particles that were positive and they were protons. Also, people discovered that they were particles that had no charge, so they discovered neutrons. What Rutherford tried to do is to actually say, is it that we have a positive dense area, or these subatomic particles that we know to date, which are called protons, neutrons, and electrons, are more localized in an atom? So via the gold foil experiment, he actually saw that the divisible units composed of positive charge concentrated in the nucleus of an atom. And this nucleus of an atom, at least in his theory, it is symbolized by that red circle that you see in the middle. That's going to be the nucleus of an atom. And in that nucleus, because it was positively charged, that's the locations of the protons. Later, people discovered that also the neutrons are located in that nucleus. Now, until that gold foil experiment, there was no knowledge or theory that will give location specifically for the electrons. So then in 1913, Niels Bohr proposed the first theory for the location of electrons in an atom. He hypothesized the electron in atoms actually live in restricted areas that he called at that time orbits. And he said that those orbits where the electrons were at were around the nucleus. Now, these orbits that he was proposing, they were actually qualified or described as quantized energy levels. And his mathematical equations were actually utilized to discuss all of this. He was thinking that these electrons in these quantized energy levels or orbits will be behaving similar to how planets are going to be orbiting around the sun. So his mathematical equations actually were good, but the problem was that they could only explain the behavior of the single electron in hydrogen. So later, about a decade later, Schrödinger in 1926 actually developed different equations that gave areas of probabilities or clouds of probability, which he actually called them, so the clouds of probability, he called them orbitals. Schrödinger's equations are so good that to date, it is how we visualize the locations of electrons in an atom. So overall, I want to introduce you to the shapes of the different probability maps that were developed by Schrödinger. You can observe that these different probability maps are designated here and that they have different shapes. I'm going to divide them and separate them using a line. And these probability maps are described by a single letter. So the first probability map that Schrödinger defined is called the S-shape orbital or probability map. The next one is the p orbital. The next one is the d orbital. And lastly, f orbital. These probability maps represent where we can find 2 electrons on each shape. So the maximum number of electrons that we can find per shape goes as follows. As you can see, we only have one illustration for the s orbital. So if we place 2 electrons here, that means that the maximum electrons that can populate an s orbital is going to be 2. In terms of the p-shaped orbital, we can place 2 here, 2 here, 2 here. So when we add 2 plus 2 plus 2, that means that in a p orbital, the maximum number of electrons that we can find is 6. If you follow the same trend, that means that in the d orbital, we can find the maximum number to be 10. In an f orbital, is going to be 14. Now, as you can observe, these probability maps, I'm just illustrating what is the maximum that can be found for the electrons in an atom. In section 3.1 of the textbook is where electron arrangements and the octet rule is actually discussed. What are electron arrangements? Or in other words, electron configurations? They're going to illustrate specifically the distribution of electrons in an atom. These shapes or probability maps that were created by the quantum mechanical model from Schrödinger actually have an order of how they are filled. All of that information is actually incorporated into the periodic table. And as we can see in the illustration that we have here, we have a sentence on the top. So this sentence is just illustrating the order in which the electrons populate the different quantized energy levels and the different orbitals in an atom. As you can see below, we have a periodic table that also illustrates the different information for energy levels, which are called shells, and the orbitals, which are called subshells. So as we can see in the periodic table, overall, the first 2 columns of the periodic table, and we have to move helium to be technically on top of beryllium only for the purpose of electron configurations, will be where we have the s orbital electrons present. Here in the middle, where we have specifically our transition metals, is where we have d orbital electrons. Next, as you can see here, from group 3A all the way to 8A, excluding helium, is specifically where we have our p orbital electrons. In the bottom, where we have the lanthanides and the actinides, we can observe that that's where the f electrons exist. Let's understand that for the purposes of this class, the f electrons is not something that we will discuss often. So how do we utilize all this information to talk about electrons of a particular atom? I want to do an example in which we actually determine what is going to be the electron configuration specifically for an element. And as an example, the element that I'm going to select to do this work with is going to be nitrogen. Nitrogen is right here in the periodic table. I am highlighting it in purple. So if we're trying to determine the electron configuration for nitrogen, the first thing that we need to determine is how many electrons nitrogen has. Because the atomic number for nitrogen is 7, that means that nitrogen, which its symbol is capital N, has 7 electrons. You can see right there the atomic number for nitrogen. Then, if I'm going to utilize this sentence in order to know where are the electrons for nitrogen, understand that I'm always going to start at the 1s level. So I write, I'm underlining this in orange so we can see how we can utilize that center. So when it comes to this, I'm going to write 1s. I know that the maximum number of electrons that I can put in an s orbital is 2. So that means that out of the 7 electrons, I already placed 2 in the 1s. So I have only 5 more electrons to place in their energy levels and their orbitals. Then I move on to the 2s, which, as you can see, is the next one. The maximum number of electrons in an s orbital is 2. So that means that I already, out of the 7, utilize 4. Remember that I'm going to place, let me just highlight it. The superscript is the number of electrons that I'm placing on those orbitals. So I already have a filled 1s orbital. I have a filled 2s orbital. So I'm going to proceed to the next orbital that I have available to me, which is the 2p. So I write 2p. I know that the 2p can hold 6 electrons maximum, but because I only have 3 left, then the last 3 electrons out of the 7 in nitrogen are placed in the 2p orbital. Let's now relate how this information, we can also obtain it from the periodic table. So I'm going to be using my laser pointer to see how we obtain the same information. The goal here, if you're utilizing the periodic table, is that you are going to count the boxes on each row that lead for you to find nitrogen. So when it comes to this, I'm going to separate each row by a red line. And then starting on the first level, then I can observe that in the first row, which is where I have 1s, I have 2 boxes. That's where the digit 1s2 comes from. On the second row, I can see that I start from left to right. On the 2s area, I have 2 boxes, 1, 2. That's where the 2s2 comes from. Next, in order for me to reach nitrogen, I have to move into the 2p area, and I count 1, 2, 3 boxes. That's why the last part of the electron configuration is 2p3. Additionally, in order for you to actually write electron configurations, you can utilize also the step ladder. I'm not utilizing that method. I just want to illustrate at least 2 methods. Use the one that is more convenient for you. Now, if you're given a specifically an electron configuration, you can determine the name and symbol for the element that it pertains to. So I'm going to do specifically problem number 2. So we can see how we can actually do this utilizing the periodic table. So here it establishes that this element is going to have the electron configuration 1s2, 2s2, 2p6, 3s2, 3p2. So when I look at the periodic table, I can follow along and count the boxes that leads to 3p2 starting from 1s2. So 1s2 is this box and this box. Then I move on to the second row. This is 2s2, 2p6, 3s2, and then we have 3p2. Another way that we can do this is by simply adding. So if you're given the electron configuration for an atom, you can add the superscripts given on each of the energy levels and the shells. So you can do 2 plus 2 plus 6 plus 2 plus 2. When you add all those values, you reach a value of 14 that, as you can see, that is the same box that we landed on the first method I utilized. So element 14, which you can see right here, that specifically is the element silicon, and its symbol is capital S, small case I. And these are the two methods of how you can find or write the electron configuration of an element, or you can actually identify the element given an electron configuration.